Hello, my name is Konstantin Malyuga. Let me present you fault-tolerant central Saga Orchestrator in RESTful architecture research. Let's start with a bird's-eye view on the current topic problem. Not so long ago, the monolith software application structure was preferable in the e-commerce industry. Creation of such applications causes tough coupling of business domains, which complicates system scalability. Evolution of this approach led to a service-oriented structure, and then to a microservices architecture that is widely used today. Encapsulation of business domains in separate applications with their own independent infrastructure allows to improve reaction to dynamically changing system load. However, such isolation brings new problems. Data consistency, which previously was supported by transactions in a database, can no longer be used if data is distributed across microservices. That is why additional instruments should be used to support consistency. Usage of sagas makes it possible to support data consistency not in an atomic change way, but in terms of eventual consistency. It is a predefined set of commands to update data in service and compensation calls to revert changes if one of the commands has failed. Every data change during Saga will be applied immediately, without additional commit procedures. Thereby, data will be modified either in all services or in none when Saga ends. There are two types of Saga implementation. In case of choreography, microservices are linked to the chain of sequential operational calls, when one service in Saga interacts directly with another. It causes complication of scalability and the Saga structure change, due to the Saga implementation is distributed across services that takes part in it. At the same time, orchestrational Saga defines services interaction through the communication provider, named Central Orchestrator. Introduction of a Central Orchestrator decouples services and defines Saga structure in one place that simplifies its management. Usage of Saga is usually correlated with relying on different message brokers that take responsibility for communication between Saga components. However, introduction of Saga to the system, which use widespread RESTful architecture for cross-service communication, is also possible. In this case, communication between services is usually organized by HTTP protocol with predefined data format payload. Saga organization through synchronous HTTP calls brings an additional issue to the fault-tolerant systems. Now, if a service which performs the request fails during the wait for a response, it will be no longer possible to retrieve the same response when the service is restored. Cluster structure allows handling unexpected central orchestrator shutdowns. The master node controls communication and replicates data to the slave nodes. If the master goes down, one of the slaves replaces it and continues the Saga based on the replicated data. To be able to repeat the command which has been sent before the master failed, REST endpoints should be implemented in idempotent manner. Introduction of cluster structure and the data replication in particular brings additional memory consumption and increases Saga duration. We propose two optimizations that can reduce the drawbacks of the fault-tolerant solution. The first one is meaning data optimization. Meaning data is request information which is only required to continue Saga process and to perform compensation calls in case of failures. Analysis of sagas during the cluster startup can be performed to define meaning data for concrete saga. Further, only meaning data will be replicated. In this example, XML response payload is shown on the left side. If Saga requires only account number and owner ID fields as saved data to be used later for commands and compensations, the next data transformation can be used. Data formats can be changed to reduce verbosity. Not required information can be ignored. and HATOS tags that are represented in links node can be also ignored, due to their redundant for the Saga flow management. After the data transformation is successfully applied, transformed data can be replicated to the other nodes. The second optimization is called optional data preservation. Preservation of data as an optional operation can reduce memory consumption and replication duration. Management of Saga process data partly or fully in RAM reduces storage load. For example, Saga process data can be preserved only when Saga fails. It allows us to find the cause of the failure later and prevents loss of time and memory for handling unnecessary information. To define optimization's impact, a model of Saga cluster is proposed. Its first part defines the duration of Saga and replication time for successful and failed sagas. That is partly presented on the current slide. The first formula shows successful Saga duration. It's defined as the sum of all local transactions and cluster data replications. Replication time itself, formula 2, is the longest time for payload transfer and preservation. It depends on meaning data coefficient k and payload size d. So the product of meaning data coefficient and payload size will be the maximum value when no meaning data optimization is used. Replication time is defined by the longest local transaction replication time. The reason for that is that replication for multiple nodes can be performed simultaneously to reduce consumption impact. As shown in the third formula, failed Saga duration depends not only on the duration of commands and their replication, but also on compensation calls and replication duration for previously executed commands. Memory requirements depends on replication coefficient, data amount, and meaning data coefficient. Since preservation can be an option, required memory for Saga data will depend on configuration. Saga data will be preserved if either optimization is disabled for any type of sagas, or RAM threshold is exceeded, or the preservation of the failed sagas data is enabled and Saga has failed. To evaluate optimization's impact, the calculation of the model was performed as for a cloud solution. For this reason, benchmarks of popular clouds were used and the performance of network and memory was defined. Final characteristics belongs to an Amazon Web Service cloud platform. Another data source of evaluation is the payload structure and size. Such values were taken from the large-scale analysis of REST APIs made by our colleagues from the University of Trento. It shows that the most popular format of data is JSON, with around 1.5 kilobytes payload size on average, and the XML with payload size of about 2.5 kilobytes. So the average payload size of 2 kilobytes was picked for the calculations. Eventually, preservation optimization have the least effect on the replication time due to the fact that network communication brings much bigger delay in relation to local storage update. That is why the two first bars with storing of only failed sagas and without storing show relatively low impact on time reduction. On the other hand, network load reduction reduces replication time consumption the most, up to 79%. The impact of meaning data optimization is represented by the last three bars. They show that replication time consumption can be reduced up to 79%. Evaluation of
memory preservation shows that the optional data preservation optimization plays the biggest role in memory consumption for replication. It reduces requirements up to 93%. The meaning data optimization itself reduces memory requirements only by 34%. The union of these optimizations reduces memory consumption by almost 96%. In this case, preservation of only failed Saga's meaning data will be performed. It's important to understand the crucial requirement of such structure. Endpoints in the potential limitation can be not so important for the system in its current state, but can become substantial later. However, implementation of Saga Central Orchestrator as cluster for RESTful systems to support failure tolerance can become a more desirable solution if proposed optimizations are used. They significantly reduce replication drawbacks, such as additional memory and time consumptions. In addition, optimization's value can be varied considering system requirements. Thank you for your attention.